Hi, everybody. Just picking up with a homework problem that we had from section 13.3 from last time we were in class together. We were talking about number 51. We had some students ask about that, where we had to write the equations of the osculating circle really drawn in for an ellipse. And, we talked through this problem where, of course, one of the formulas for kappa that we had was just for a function of x. Really, this is like a two-dimensional graph. Normally, this is a wonderful formula that we can use whenever we need to find curvature. But we talked about how here in this particular problem, the osculating circle is always going to have this relationship that the curvature k is equal to 1 over the radius, or another way of looking at it, the radius is 1 over k, or kappa, I should say. But, as we're trying to find kappa, the problem that we talked about was that f prime at the point 2 comma 0, f prime didn't even exist at that point. So this formula for kappa, which is normally so incredibly helpful, is not going to be able to be used for that point in question. So if you ever see that you have a vertical tangent line on a graph, in other words, you know that your first derivative would be undefined if you were to substitute that point in question in, you have to go about this problem in a different manner. And like I had mentioned in class, we have to use parametric equations to make this work. And, I began to talk about it, but I didn't work it through in detail, and I'd like to do that for you now. Let's review. We've got this ellipse, and we've got x squared over 4 plus y squared over 9 equals 1. And, of course, we even, originally when we were working this problem out as a function, we said that we could just look at y being the positive. We could solve for y, and we could have an equation for y. But the whole problem, like I said, was that our first derivative, even with this function, would be undefined at 2 comma 0. So here's another way to look at this. We could say x over 2 squared plus y over 3 squared is equal to 1. We could very nicely now come up with this kind of a parametric equation. We could say x is equal to 2 cosine of t, and y would equal 3 sine of t. And the reason why we can do this is, of course, if we were dividing both sides by 2 right here, we'd have the cosine of t. If we were dividing both sides by 3, we'd have y over 3 equals the sine of t. And of course, we know that cosine squared of t plus sine squared of t equals 1. And that would mean that we'd have x over 2 quantity squared plus y over 3 quantity squared equals 1. It's kind of like reminiscent of x equals r cosine of theta and y equals r sine of theta. You could see that you've got, a different r value. It's not going to be the same for both, but this is how you can make this work out for an ellipse. I want to be very clear. This is not the only way you could use parametric equations here. It's so important to see that. But suffice it to say, if you were to say, what's r of t? Well, r of t then could be 2 cosine of t, 3 sine of t, and, that would thankfully allow you to get a very nice graph, even if you went to parametric mode. And if you were to, let t equals 0, you could see you'd be at the vector 2 comma 0. You'd be right here, at the point 2 comma 0. And, at pi over 2, you could see you'd be up at 0 comma 3 and so forth. So that's kind of nice. Look, let's real quickly talk about r prime of t. You could say, well, if I took r prime of t, we'd get negative 2 sine of t, 3 cosine of t. And by the way, we're going to go one step further too. We're going to go r double prime of t. And r double prime, if we took that second derivative, we'd be at negative 2 cosine of t, negative 3 sine of t. Now, of course, we also want to make this note that at t equals 0, r of 0 would be the vector 2 comma 0. You know, you can plug 0 in for both of these. Cosine of 0 is 1, sine of 0 is 0. R prime of 0, in a similar way, you could say it would be 0 comma 3. And r double prime of 0, likewise, we could work out to be negative 2 comma 0. So I'm doing that really because what's driving this whole process, look, in what I've highlighted, for the point 2 comma 0, I can't use that formula. It's so frustrating that we can't do that. What do we have to do instead? Well, we're going to have to use this formula of kappa is going to be the cross product of r prime, or r prime of t, r double prime of t, and we're going to need its magnitude. And then we're going to divide by r prime of t, cubing that. And that means if we want the curvature at 0, we're going to really say, well, take r prime of 0 and cross that with r double prime of 0. And then underneath, we're going to have r prime of 0. This magnitude, of course, we've got the magnitude up on top, and we're going to cube that. Well, it won't take you too long for kids to, even using their 89, to quickly say, now wait a minute, with a cross product that I have here with 0, 3, and negative 2, 0, kids can get very upset with that and say, now wait a minute, if I try to work that thing out, if I try to get that 89 up, and we can bring that up here, we can say, well, let's get our catalog, and we'll get our cross product, and we'll say the cross product of, and if we were to type in 0 comma 3 comma, and then if we went from negative 2, didn't mean to make the negative show up twice, and make that negative 2 comma 0, you can see as you try to compute that, what's surprising is you get a 006. Now, it's important to note that the calculator has interpreted that, has definitely interpreted that as actually being like the vector 0, 3, 0 crossed with negative 2, 0, 0. So what are we getting at? We're seeing that that thing would equal 0, 0, 6. Wow. So, it's like 0i plus 0j plus 6k, evidently. So, just bringing that back up there. So you could say, well, what's the length of this thing? Well, the length of that thing, amazingly, do the Pythagorean theorem. It's 0 squared plus 0 squared plus 6 squared. You don't even need to do the Pythagorean theorem. You just say that arrow has a length of 6, right? Down below, you'd say, well, what about r prime of 0? That's the vector 0 comma 3. Well, what's its length? Well, 0 squared plus 3 squared, that's 9, and take the square root of that, same thing. You'll get just a 3. But don't forget, you're also going to have to cube it, right? 3 to the third. So that's 6 all over 27. That's going to be 2/9. That's your kappa. That's your curvature. Now I can say r is the reciprocal of kappa. R is going to be, you can see 9 over 2. Now, if you think about it, that's, 4.5 or 4.5. Well, if we went back up to this circle, and you could say right here is 2, here's a 2. If you're starting right here, and if you know that this is where your circle is going to be drawn, you could say, well, I've got to have my circle have its radius 4.5 steps away. So I'm going to go 2 steps, another 2, and then a half. So this would be -2.5 where the center of my circle would be. That way you would get 4.5 for your radius. Now, of course, that would really be at -5/2. And, of course, you could also just do 2 minus, 4.5. And, what are you going to get? You're going to get -2.5, right? Well, that's the center of your circle. It's going to be at, we're going to have -5/2, 0. Our radius is going to be 9/2. You write this equation out. You can check the back of the book, and it will get you this equation of your osculating circle. Just wanted to talk you through that. I know it's one thing for us to, just do a parametrization and, everything's going to work out. This is actually in detail how to get that osculating circle. Now, I do want to make one final comment before the video is over, because sometimes what's going to happen is kids are going to look at this equation that we had earlier, and that equation, of course, was 9x squared plus 4y squared equals 36. And one parametrization that we had, and it was a great one, was this right here. But rest assured, what we could do is, but the bottom line is, we could make a whole bunch of parametrizations. And I guess what I just want to, call to your attention is that we could, in theory, say, let's let x equal t. And you're free to do that. You're certainly free to do that. And, then what? Well, you can go ahead and solve. And you can say 4y squared equals 36 minus 9t squared. You can divide by 4. And, maybe this looks way different. Again, maybe you only want to deal with the top half of, what you were graphing a moment ago. Maybe you only want y to be that positive. What am I getting at? Here's another parametrization that would work. You could find r prime. You could find r double prime. And this time, if you were looking for the point 2, 0, you'd be plugging in t equals 2. You could take your derivative, first derivative, second derivative. You can do your cross product the same way. So I just want to let you know that there are many ways you can work with parametric equations. Yeah, the trig is clever, but you do have other options. I hope this helps. We'll talk to you soon.